Professor Ionides got his bachelor and master degree in mathematics from Cambridge University, and then he received his PhD degree in statistics from Berkeley, supervised by Professor David Green. And then he was a visiting assistant professor at the University of Chicago, and then he joined the University of Michigan. So Professor Ionides has he works on the statistical analysis of dynamic systems with application to biological sciences, public health, and epidemiology, especially in disease transmission. So he has made groundbreaking and highly influential contributions to the theory, methodology, and applications of often observed stochastic dynamic systems. These works bridge the gap between mathematical biology and the statistical inference methodology. So he is currently a fellow of the American Association for the Advancement of Science and a fellow of the International Statistical Institute. So he has definitely received numerous grants and published numerous fantastic papers. Please join me in welcoming our speaker.
Okay, so thanks for the kind introduction, and thanks for the invitation to come speak this great department. It's good to see some old friends and meet some new ones. So I have quite a long title: Iterated Block Particle Filter for Inference on Coupled Dynamic Systems with Shared and Unit-Specific Parameters. And I think I'm going to try and explain that it's sometimes when you have a long title, that means it's like a very sort of specific niche thing. But I think this talk has a lot of applications. This is a topic I've been working on for many years with Patricia and other students, Jesse, Caduce, Gfan. Gfan's going to be joining this department as a PhD student in the fall. He's great, and my long-term collaborator Aaron King. Okay, so the goal of this talk is to carry out full information likelihood-based inference for general partially observed market processes. This means that it's nonlinear, it's non-Gaussian, and you only observe it with some noisy function. And when you can do theory for these things, you can also try to do data analysis. If you try to do data analysis, you're going to be limited by software. The particular software package we've been developing to implement our methods and other people's methods, as long as we can figure out how to implement them, is the R package StatPump. And so that is our goal, is to develop methods and software and try using them. And so I'm going to be telling you about the iterative block particle filter, and my motivation for doing that is because for the problems that I'm going to show you about, I think it's currently the best thing we know how to do. And so there's a sort of methodological problem, which is just to access the likelihood function and maximize it for these things. But of course, that's only the start for data analysis. You then want to talk about things like, if the model is statistically adequate, how do you know if it's good? How do you know if it needs more work? Okay, so this slide is a little bit of a history on the problem, and it's sort of a history of what I've been working on for the last couple of decades. I'm sort of excited to be giving this talk because it's kind of on a problem that I kind of wanted to solve in my PhD thesis, and then I realized it was way too hard, and so I had to do something easier. But it's like I've been chipping away at bits of it for a long time. Anyway, so back in 2001, when I was working on just simpler kind of time series versions of this problem, there was I think a well-written, influential review paper in Science magazine by Otto Bjornstad and Brian Grenfell, and I think it's still worth reading. It's worth coming back to if you're interested in this area. Anyway, they identified various kind of challenges in nonlinear time series analysis, basically. it had become obvious by that point that you wanted to combine measurement noise and process noise, that just having one of those forms of stochasticity isn't quite enough. You want to include covariates in mechanistically plausible ways. You want continuous time models. You want to be able to kind of model interactions between components of the system in scientifically plausible ways. And you have to accept the fact that you're not going to be able to observe everything you want to model. Then you may have space-time data, you may have genetic data. But so these problems 1 to 5 are largely solved from a methodological perspective. That's been a lot of what's been happening over the last couple of decades. So 6 and 7 are kind of currently the research edge, and this talk is on 6, spatiotemporal dynamics. And this is an example of the kind of data that is motivating us. This is weekly measles case reports in England and Wales. It's a classical data set. These data are pre-vaccination from 1950 to 1965 odd. The scale is log cases plus 1, natural logarithm. So 8 corresponds to e to the 8, which is about 3,000. And so you see here the data as outbreaks of measles typically every 2 years in London. Let's try my hand at a pointer. And London is quite like clockwork in this particular time interval. There's outbreaks every 2nd year. So when there's an outbreak, it depletes the susceptible pool, and it takes a couple of more years for new recruits, which typically births, to come and replenish the susceptible pool, so you get another outbreak. You see in smaller towns the dynamics are more messy. You have local fade outs and so on, and we've all got very used to looking at this kind of data, right? During the COVID pandemic. The measles is just an easier situation to get started on than COVID. It was quite stationary in this time period. There was no vaccination. It was just the system running on its own. And measles does not have a relevant strain structure. So measles has perfect cross immunity between strains. So you can ignore those sort of issues of different alpha, beta, gamma types, whatever, coming through. Okay, so here we have specifically, we have the 10 largest towns, and we have 10 sort of randomly selected smaller towns. Okay, so just to again put some context to what we're going to try to do, we're looking at spatiotemporal data, but I'm coming at that more from a time series direction. If you just have one unit or one town, you call that a time series problem. Probably if you had 2 or 3 towns, you might think of it as time series as well. A multivariate time series in that case. And if you have a fairly large collection of towns, but you don't consider dynamic coupling, then you would call that panel data analysis. And if you do allow coupling, it's called a spatiotemporal model. And in this kind of population biology, the spatiotemporal it's a little bit different from some other, say, geophysical contexts. Like you might have 10, 50, 100 towns, but we're not going to have. I wasn't sure if this was showing up on everybody else. Right, you're not going to have. You're not going to have a massive number of units. So there's no linearity, stochasticity, and quite long time interval, but not a massive number of units. And that's the metapopulation analysis. We want to be able to consider arbitrary dynamic models. Why do we want to be able to do that? It's basically because the scientists can't decide, they can't agree on a model. They want us to help them choose a model, and so to be limited by the scientific creativity. If some scientist says it would be really interesting to consider that, we want to be able to say, yeah, well, here's its likelihood, this is how it fits the data or doesn't fit the data. And so we tend to focus on methodology that needs a simulator from the model, but not nice closed form expressions of densities. We call that plug and play because the simulator kind of gets plugged into the algorithm. Some algorithms have this property, other algorithms don't have this property. If you have an algorithm with this property, not only it's easy to apply to fairly general models, it's also relatively easy to write general purpose software for it. So when we're writing our software package, StatPomp, if somebody has a plug and play algorithm, we can very easily implement it and try it. And if it requires some custom properties of the model, then it's very hard to implement in general software. We want to do statistically efficient inference to extract all the information from the data in these kind of disease modeling situations and various other kind of ecological situations. You can view disease as just one ecological system, right, where there's just two species, the pathogen and you. We're normally data starved. We know there's biological complexity. We want to write a fairly complex model, and yet we only have relatively limited data. So things that you might do that rely on summary statistics, like method of moments or approximate Bayesian computing, are kind of hard to do. If you have a full Bayesian solution, that would be nice. I guess full Bayesian and maximum likelihood are sort of siblings in some sense. They both work with the full likelihood. Okay, so for time series, where we have these iterative filtering algorithms that allow master's level statisticians to do plug and play likelihood-based inference for arbitrary time series models. And so I teach this class every year, not this semester because happily I'm on sabbatical. But anyway, my task is to get a class of 50 odd students each doing their nonlinear time series analysis. And so the science may be hard, right? The models are nonlinear, they're hard to understand. The statistics is becoming more routine in that case. So for panel data, we have high dimensional data, but we just don't have the coupling. This is a natural thing to do. If you can avoid coupling, you do avoid coupling. Just like if you can make do with a linear Gaussian model, you do, right? You only go to the nonlinear case when you're convinced there's something essential to the system that you can't capture with a linear Gaussian. So you might be able to find cunning ways to sort of decouple by conditioning on something. And in that case, you have a panel data problem, and these iterative filtering algorithms can be extended to panel data via panel iterative filtering, and that's implemented in the panel pump package. One thing that starts coming up when you do that, it's kind of, I find fitting just panel models to mechanistic data. There are already a lot of kind of open data analysis problems. Fitting kind of arbitrary mechanistic panel models is kind of new. You have to choose which parameters should be shared and which should be unit specific. And then, of course, if some of your parameters are distinct for each town, then you suddenly have a lot of parameters to deal with. I'm not going to talk too much more about panel pump because I want to get onto the fully coupled system. Now, even if you have a way of decoupling, then how do you know if it was successful or not? Well, you kind of want to, ideally, you would be able to solve the fully coupled problem, perhaps with more computer time and more effort, and then see what you'd lost by simplifying the problem. If you can't solve the full problem, it's hard to know what you've lost by simplifying it. So anyway, we want to work with fully coupled models, but the thing that has really helped us in simpler like time series and panel situations is the particle filter, which is really a wonderfully robust and easy and simple algorithm for nonlinear, partially observed systems. It'll give you the likelihood, but it really, although it doesn't struggle with nonlinearity, it does struggle with high dimension. And so practically, once you have more than 2 or 3 towns, you can't practically run a particle filter. So you need to do something scalable. And I've been working on that for a while. Other people have been working on that. The bagged filter is something we developed, and the guided intermediate resampling filter. The Ensemble Kalman filter is a major option, and I know some people here have been developing that. Another thing that's been introduced recently is the block particle filter, and that's going to be kind of the thing we're going to focus on today. Now, filters estimate latent states. They evaluate the likelihood. There's a step going from that to inference. Somehow you either have to maximize the likelihood or you have to carry on some Bayesian calculation. And iterated filtering is just a way to coerce a filter into doing maximization. So if you give me a filter, I can generally adapt it to an iterated filter that's going to do a maximization. And so here you go. Here's some algorithms. I'm not going to talk about them all. They're all implemented in the SPATPOMP R package. And so I spent a lot of time developing these bagged filters, and then one of the referees at JASA said, you really ought to compare with a block particle filter. And we hadn't actually done that because the authors of the block particle filter had basically said, we have nice theory, but we don't expect our algorithm to work well in practice. And we took that at face value and we hadn't implemented it. And then when we did implement it, it turned out that on these disease models, not on all models, but on the particular structure of these metapopulation models, the block particle filter was basically beating the competition. So this is the sort of thing you do when you want to compare different methods, right? You need a simulation study because that's easier to compare with, and you try the different methods. It's really helpful to look at different numbers of units. Here, U is the number of units, which is the number of towns, and when U is very small, here where U is sort of 1, 2, or 3, you basically can't beat a particle filter. It, theoretically it converges and it's a great algorithm, but you can see the particle filter nosedive very soon. Basically everything other than the particle filter has to make some sort of approximation. There's going to be some trade-off that you have to make. You're not going to get a sort of perfectly consistent estimate of the maximum likelihood, but you can kind of tell from the small values of U how much is lost. And then you can tell as U increases how scalable your algorithm is. On this particular measles example, the Ensemble Kalman filter, which sort of contains within it something like a Gaussian approximation. It's called a non-Gaussian filter, but its update rule is based on Gaussian principles. And so on this highly non-Gaussian problem, it doesn't do all that well. Okay. So here's sort of a connection between the kind of simulation study and the data. These models fit measles data really remarkably well. I haven't given you the details of the model because I don't want to overwhelm you guys with lots of equations, but I have to always check the caption to remind myself which is the data and which is the simulation. And so I guess that means the simulation is a decent reflection. Okay, here B is the data and A is the simulation. But you see, You see these in both cases, the peaks roughly every 2 years, but some cities break from that. That's the basic story. Okay. So when you're writing down these models, you have to figure out what biological complexities you need to explain everything that's going on. It turns out that putting term time transmission, just a transmission that's higher in when school is in, lower when school is out, that is kind of the key for getting good models for these measles data. And that's also one of the triumphs of modeling. Like, what drives seasonality of diseases has for a long time been hard to work out. It is a challenge for every new disease. And basically the way it was worked out in measles was using by fitting models of this kind. So there's disease latency, there's a duration of infection, there's initial values that turn out to be important. Possibly there's a cohort effect. So measles is a childhood disease. Kids really are getting infected in school, and they all arrive in school the start of September, regardless of when their birthday is. So it's not like the new births are drifting gradually in. And so that might be an important effect. You can add it to the model, see if it's an important effect. There's a mixing exponent, I to the alpha, which is supposed to model inhomogeneity. These models, I haven't actually written out the model, but during the pandemic, I guess everybody saw these SEIR model. Okay. Let's try again. That's a whole lot better. So susceptible goes to exposed, which is really a latent state, goes to infected, goes to removed. And that's the basic dynamics, right? And then you just need to write equations for how people are transitioning between these states. And then there's a measurement model, and then there's going to be some model for movement. In more recent times, you might try to use cell phone data or something for this historical data. And actually, for many modern analyses too, people use these things called gravity models. It's called the gravity model because you just model the movement of people. The movement between two towns is proportional to the product of the populations and inversely proportional to the distance squared. So it has the same formula as Newton's gravity rule. Including overdispersion turns out to be very important in these models if you want them to fit the data. If you just write the simple Markov chain models, then you get these Poisson-like models where the variance is proportional to the mean, and if you just fit the data, do a whole lot better if you allow overdispersion, and that's really a separate talk, but it's an important thing. And you need overdispersion both in the dynamics, which is the process model, and in the measurement, if you want to explain this data. And then this model is basically a previous model plus the coupling. Okay, and on this model, the block particle filter worked quickly, easily, and reliably, and that kind of was very promising, considering how hard we've been working for results that were rather slow and unreliable for other filters. The block particle filter has theoretical support in some situations. I just alluded earlier to the Rebeschini-Van Handel paper in 2015, where they basically showed that under certain asymptotic situations, then you can beat the curse of dimensionality with a block particle filter. And that motivated us to develop an iterative block particle filter for parameter estimation, and that's something Patricia worked on, and that's just appeared in JMLR, and Patricia was able to get theoretical guarantees in the specific case where all parameters are unit specific, and that kind of theoretical support really motivates one to then go a little bit further and fit situations where maybe some parameters are shared between towns and some are unit specific. And so in some ways it's surprising the block particle filter wasn't developed earlier, considering it's, I'll tell you what the algorithm is. I haven't told you what it is yet, but it's a fairly simple, almost obvious algorithm. And in fact, it was proposed before. I guess many good ideas are proposed more than once. It was a called factored particle filter. It appeared in the engineering literature, but it didn't really take off. I think doing space-time inference is hard. Even if you have a good algorithm, the models are complex and it's hard. And so maybe it's really the thing that's letting us do more data analysis now is we not only have these algorithms, we have the iterative version of it, and we have the SPAT prompt software that lets you investigate data using these algorithms. And so maybe these things just weren't ready to have their time yet. So I'm overdue to tell you what a block particle filter is, in case Patricia hasn't explained it adequately to you before. Okay, so to understand a particle filter, sometimes it's helpful to think of an evolutionary analogy. So we're used to thinking of Darwinian evolution, where you have mutation and fitness, and then natural selection acts on the fitness. The particle filter can be thought of as doing that in the context of the dynamic model, where the mutation is the stochastic dynamics, the fitness is the measurement weight that tells you how consistent your latent variable is with the data. And then the natural selection is like a resampling. Particles that are consistent with the data get resampled and propagate. And okay, so that's just a sort of heuristic overview to the particle filter. You can think of it, in fact, as there's this whole class of evolutionary algorithms. So you can think of the particle filter as an evolutionary algorithm. This happens to be one with good mathematical properties. It gives an unbiased likelihood estimate and consistent latent state distribution as the number of particles increases. So now I can tell you what a block particle filter is, and the blocks are a partition of the metapopulation units. And so in the context of the measles data that I showed you, you can think of a block as just what's going on in one city. That's sort of the natural unit. A metapopulation, almost by definition, is a collection of concentrated populations with space in between them where not all that much happens. Okay, so the block particle filter kind of adds a, in the biological analogy, it adds the sense of a chromosome. So you have fitness for each chromosome, you select each chromosome, you recombine chromosomes, and that lets you search effectively with a much longer amount of genetic material than you can do without a chromosome structure. So blocks are segments of the full state which can be reassorted between particles at the resampling state. And so the block particle filter is just a particle filter with block where you resample blocks separately. Okay, so here we're looking at evaluating the likelihood in different ways for simulations of the measles model. We're not doing an iterative block particle filter yet. We're just doing a block particle filter for likelihood evaluation. And we're comparing it with the thing that we previously worked hard to develop thought was kind of fancy and cool, the adapted bag filter. And C is the Ensemble Kalman filter. And so at this point, we worked very hard on A, we worked less hard on B. This was just the more or less out of the box block particle filter. And A and B could both estimate the parameter. If we just do like a slice through the likelihood, you see that the likelihood gets maximized at the truth, give or take a confidence interval. So that's all behaving as it should. The Ensemble Kalman filter, it turns out, has some considerable bias in this task. This task is a much easier task than computing a profile likelihood for real data, which is what you'd have to do for real inference, because here it's simulation, we're just changing one variable. We don't have to, for a full profile, you have to maximize out over all the nuisance parameters. But here, we just treat the nuisance parameters as known in a simulation study. Okay. So it's worth thinking about the Ensemble Kalman filter people here have. If you have a really large problem, you may have no choice but to do an Ensemble Kalman filter. I'd like to suggest to you that it's more dependent on approximate Gaussianity than is sometimes supposed. That's my experience. The Gaussian-inspired update rule is sort of similar to an extended Kalman filter with a little twist. If you have a low-dimensional linear dynamic biological system, you probably would not use a extended Kalman filter anymore. You'd use a particle filter. And previously, people have used the Ensemble Kalman filter for higher dimensional systems, but I think that was partly because of lack of an alternative. It's actually possible for quite simple systems to defeat an Ensemble Kalman filter if they're non-Gaussian enough. For instance, if the information is in conditional variances rather than conditional means, well, the Gaussian density the Gaussian joint multivariate Gaussian just doesn't have that feature, so it can't explain it. If you're getting to systems much bigger than the systems I'm going to show you, you may well, again, have no choice but the Ensemble Kalman filter. We're going to have reasonably large numbers of parameters. We're going to have to estimate at least some parameters for each unit. And some of the dynamic parameters may also have to be unit specific. I guess the data analysis is going to tell us that. And then, of course, you have hundreds, possibly thousands of estimated parameters. So you may have high dimensionality in the parameter space. You may not, right? It may be that the high dimensionality is primarily in the latent variable and the measurement space, and the number of parameters doesn't necessarily have to be too large. But one thing that I want to convey to you is that actually doing data analysis with these models, even if you just have 5 or 10 units, this is stuff that couldn't be done before. And so any system where space and time are important in these coupled biological systems, we've got work to do. Okay. I've told you about the block particle filter. I haven't really told you what the iterated block particle filter is. And the basic idea of iteration to maximize the likelihood is that you perturb the parameters, and then when the evolutionary algorithm is finding states compatible with the data, you've thrown the perturbed parameters into the states, and then it can simultaneously select parameters that are consistent with the data. And then so the filtering does a little bit of parameter estimation, but the catch is that you've perturbed the model. It's not quite the model you actually wanted to estimate. And so what you have to do, you have to make the perturbation smaller and smaller. And then you keep iterating this filtering, and with any luck, you get near the maximum likelihood estimate. And the theory is there to tell you that if in some asymptotic sense, as things get large enough, that could happen. Okay, so how does this play out in practice? I'm going to show you some data for these 20 cities of measles, and yeah, the first column here is the simulation study, which it's always a bit hard to look at other people's simulation studies because the conclusion normally is yes, the algorithm works on simulated data. What happens on the UK towns? What we had to do multiple stages of this iterative filtering, and at each step you start somewhere and you go to somewhere. This line is what happens if your maximization actually doesn't even help you. And so in the first iteration, you do a lot of climbing. But it turns out when you do more iterations, you're still not quite there at what you think is the maximum. And so eventually, if you work hard, you get to maximize the likelihood up to a certain amount of numerical approximation. And so this was kind of interesting for us because we wanted to do this sort of analysis and just hadn't been able to for a long time. And again, the top panel here is on simulated data, and what's going on here in case C, we don't have coupling. We just do a simple thing to avoid coupling just by giving each city a certain background level of immigration. And that would be a sort of standard thing to do in disease modeling if you can't fit a fully coupled model. Well, what we see from the simulation study is that if the true model is coupled and you fit a model that isn't coupled, then you can work out that your model is missing something. It's kind of interesting to us because when we do the same thing to the actual data, we actually find that this model, which sort of avoids the coupling, actually fits as well as the coupled model. And to my mind, this reflects a limitation of the gravity model. The gravity model isn't really giving you an edge over simpler things. I think this is a good research question. Basically, people know that the gravity model has limitations, but my claim is that what we've shown here is that we have a tool that if you can be perfectly well applied to any other distance model, and when you find something for which you get a substantial edge over naive models, then you will have made some concrete progress on good movement models for measles. This is basically what I've said. So yeah, that's this is moving on to what we're currently researching on. So here are some other kind of research questions we're leading on to. This is kind of interesting. What's going on here is that when you fit these disease models, sometimes there are sometimes a parameter which biologically you would think would be the same for every city, in fact, varies across cities. And the first thing to do, again, is to kind of assemble the evidence for that. And this is kind of the evidence. I'm not going to try and explain every number on this table. You'll be glad to hear. But I've highlighted the one number that I want to focus on, which is, it turns out that infectious period, which I've called IP along the top, is highly positively, estimated infectious period is highly positively correlated with city size in these data. And that's probably not really a biological feature. It's probably, you might think of it as more of a model misspecification feature. Maybe for some reason, larger cities are less homogeneous. It wouldn't surprise you. In a small city, you know a larger fraction of the city. In London, you never even talk to somebody who lives the other side of the river from you. And so maybe that's what's going on. And again, the sort of main point that I'm trying to convey here is that by sort of carefully fitting these models by maximum likelihood, you can clarify these issues. And now we're kind of working on resolving some of them. Here's another analysis I've been working on recently on cholera in Haiti in 2011 to 2019. There was 2010 to 2019. I've got here. There was a big cholera outbreak in Haiti, and people were trying to figure out vaccination strategies. And so here we have data on case counts in the 10 departments. And what we did was we reanalyzed a rather nice analysis that was trying to inform vaccination policies. And what they did was they got 4 really good epidemiological modeling groups to analyze this question using 4 of the sort of different but state-of-the-art methods, and they were going to guide vaccination plans. And so they did a stochastic model, a sort of partially observed Markov process model at a national level, an ODE that's spatially explicit, a stochastic model that's spatially explicit, and an agent-based model that was one of these massive complicated things explaining what everybody in Haiti did. Well, it's kind of interesting because they all got it wrong, despite agreeing with each other. And so it's obviously easier to use hindsight, right? Because we now know the answer. So even if we can work out a way they could have got it right, that doesn't mean we could have known at the time that one was going to be right and the other was going to be wrong. But our idea is that by fitting models rigorously to data, looking at their likelihood, looking at their model fit, looking at the outliers and so on, you can have a better chance of saying a priori what's going on. So really the question here was, do you need to vaccinate, or is the disease going away on its own? And so what happens is that the epidemic arrives, the cholera arrives, there's this massive outbreak, and then it starts to decrease. And it can start to decrease for different reasons, right? It can start to decrease because there's a depletion of susceptibles, and so there's like immunity grown up, or it can decrease because of some treatment, or bringing in clean water and so on. And so kind of the question is, when you're seeing yourself somewhere around this time point, we can see it's decreasing. We want to kick it out. Do we need a vaccination campaign, or is it going to go away on its own? And so this can be this can be captured by models. And again, I don't think I'm going to have time to go heavily into the details, and I'm running out of time. One thing that I want to share with you guys is kind of simple strategy. We found it's really important to compare log likelihoods of the models with just some dumb out-of-the-box statistical benchmarks, typically a log ARMA benchmark. And if you do that, which they didn't, you tend to find that the models they found have likelihoods that are actually lower than just fitting an ARMA model. Now, that sounds bad, but it's not really bad because an ARMA model won't inform vaccination policy, right? You need to have all these mechanisms in the model so that the model can tell you what to do. But these mechanisms, they add constraints to fitting the data at the same time as hopefully explaining the data. And it's really not unusual for the constraints you add to mean that your model doesn't fit the data anymore. And this is particularly the case with the ODE model. Model 2 is an ordinary differential equation model. Any ordinary differential equation model for this data is just not going to fit as well as an ARMA model. If you have sort of more mechanistic models and you work on it carefully and you do the things that I've been telling you about earlier in this talk, then eventually you can beat an ARMA benchmark as well as having mechanistically explainable data. That is really a quick summary. Yeah, I was maybe going to tell you a bit about COVID, but I don't think I have time, so I shall just, as I say, this is really what we're doing. We've given you a flavor of what I'm doing now. We're going to keep doing it. Well, thank you for your attention.
For measles data, what were the initial goals of analysis and how one would come up with nonlinear model in that situation?
Good. So measles has been, this is a very sort of canonical data analysis. So it's a canonical data set, right? It's been very widely studied. So we use it a little bit as a test problem, but you might be able to get some new insights. I'm not sure if you were saying originally when people started analyzing measles, or originally when we started looking at this particular analysis. I would say, so one thing that people were really interested in extracting from the measles data back in the kind of 1980s and 1990s, there was people trying to understand how well mathematical models could fit biological systems. It was like a poster child for that. And then people were trying to work out, say, is mathematical theory of chaos useful for studying epidemics? And that was like in the 80s and early 90s, that was kind of a hot topic. In the end, people figured out that it's not really chaos. It's a mixture of nonlinearity and stochasticity. And so there's many other questions you can ask of measles. And there's this guy, Brian Grenfell at Princeton, and if there's any question that can be asked of measles, he's probably asked it on these data.
So could you please talk a little bit about that COVID-19 analysis? I think it's quite important.
Yeah, so I have to, when, you know, during the pandemic, I was busy developing methods and just hunkering down, trying to run our own undergraduate program at Michigan. I wasn't actually applying data analysis in the pandemic. I'm glad many other people are doing that, but I finally started looking at some COVID data. And so again, this is like this is a retrospective analysis where you go back and you look at people were using space-time data early in the pandemic to try to figure out what on earth was going on. And so one of the best examples of this, a highly cited influential paper in Science magazine by Li et al., a group from Columbia, used an iterated Ensemble Kalman filter to fit a what we would call a SPAT bomb, a spatial temporal partially observed marker process. And so we were kind of interested if you get the discretization right and you use an iterated block particle filter rather than an ensemble Kalman filter, does that actually kind of change the story? We're still working on this data analysis. It's hard to compare simulations, but we found it sort of consistent with this story that oftentimes there's some value to looking beyond the ensemble Kalman filter. EnKF does not deal very well with discreteness because of its sort of Gaussian approximation. In this particular data, there are many zeros because as COVID was spreading through China, most of the places it hadn't got to yet, and then near the end of this time frame, it's in more places. And so again, you can try extending ensemble Kalman filter to count data, and that's what your colleague here was doing. And maybe I forget who else was on that paper. But you now have another option, which is you can apply an iterated block particle filter to it.
Do you have any? If not, let's check our